Next speaker is Helmut Hauser from the University of Bristol, where he's lecturing right now. He actually is one of a few people exploring the basic modeling of morphological computation. And today he will talk about adaptive morphologies, which might also be seen as a more general concept than soft robotics. So soft robots are actually robots able to adapt morphology. But I don't lose more time, and I give the floor to Helmut. Thank you for accepting the invitation, and please.
Thank you, Fabio. Thank you for the invitation, for this really nice introduction. I just want to share the screen. Okay. Can you see the slides? Okay.
Yeah.
Okay, so as Fabio already said in the introduction, I'm going to talk today about a concept which is changing the morphology, and we refer to that usually as morphosis. And in connection to morphological computation, which also has been discussed in previous lectures here in the ShanghAI lecture, also in the talk of Fabio, I see morphosis actually as what I would call the next level in morphological computation. And I hope by the end of my presentation, you're going to see why I think that's the case. Now, I assume that everybody knows what morphological computation is. Nevertheless, I think it's a good idea that I provide you with my own kind of, I wouldn't call it definition, but description, so that you understand where I'm coming from. So I see morphological computation as a general concept which is based on observations in nature, that we can see that biological systems, and by that I not only mean animals, but also plants, cellular structures, even on the molecular level, that you can see that the morphology plays a very important role, and one could see that as a computation that is carried out by the morphology, which is in some form beneficial for the agent there. Now, usually I give also some kind of examples so that people know how I see morphological computation. And usually the first example that I start with in my dogs is the slinky. That's this one. It's nothing else than some kind of spiral spring. It's actually a toy, and you can do all kind of fun stuff with that. And one is, for example, you can put it on a treadmill. You can incline the treadmill with a certain angle. You give it an initial pull, and you start the treadmill, and you can see something very beautiful. And Nathan, if you can please start the video. So what you can see here, you get a locomotion, and it looks natural and very beautiful. An interesting part happens when it gets to the side where the friction is different. So you can see it slips away and reacts properly by going back into its normal trajectory. Now, the interesting part here is there is no electronics, no sensors, no controller, no brain whatsoever. It's pure mechanical interaction. And this kind of behavior actually you want to see in a robot, reacting properly if there is a change in environment, and do it in a robust way, and keeping, in this case, locomoting in a robust way. So that's very promising from the viewpoint of morphological computation. Now, I would also like to have a look at that from a more theoretical point of view, and I show you a simple thought experiment. So let's assume we have some kind of flat surface with no friction whatsoever, and on top of that we put a little ball with a mass, and we want to have it at a desired position. So this means we're going to talk here about some kind of control problem. And if we have some temporary perturbation, some kind of forces applied to that mass, what will happen? Of course, there's no friction. The ball would roll on over into infinity, basically. Now, we can then define a position error. So what is the actual position, where it should be, and we can say, well, the error is that big. Now, how do you control this system? Well, in a classical robotic approach, you would use an external feedback loop which forces the system back into its desired position. So what do you need for that? Well, of course, you need some kind of controller, which is some kind of computer, some central processor unit. You need the information which you can retrieve through a sensor of the actual position of our mass. But that's not enough. In order to calculate the error, you also have to know the reference position. So that's an information that you have to provide for the controller. And based on this information, it's going to compute the appropriate feedback that it has to apply, the appropriate force it has to apply to bring it back. So if I'm farther away, I have to apply a bigger force than when I'm closer to the desired position. And of course, you need also some kind of actuation, which is applying this force to the system. So if you would like to implement it in a real physical system, there are a couple of things which might be an issue. First of all, if you have a sensor, you're going to have to deal with noise, with drifts, with aging. So all these kind of problems that you encounter when using sensors. Another problem might be in the controller loop itself. So there is definitely going to be a delay. And if the delay is too long, it can render the system unstable. Actually, in linear control theory, it's well known, if you have a feedback loop and the delay is too long, you can render actually a stable system into an unstable system. And finally, you also need some external energy in order to provide this force to bring this little ball back into its position. Now you can see it's very complex. You have this artificial control loop with all these issues just to bring the ball back into its position. So it seems to be a little bit an overkill. Now, if we look at the problem from the viewpoint of morphological computation, can we think about some kind of morphology, some physical, mechanical solution which actually does the same job? Well, it's quite easy, and I guess most of you have thought about that already. You just add to the mass a simple damper and spring. So that's very straightforward, and it's really nice because you can do it in such a way that the resting length, so where the energy is zero in the system, its preferred position, is in such a way that it's exactly the length between the point of attachment and the actual desired position. Another beautiful thing here is you can see you have an appropriate force. So if I'm farther away, the restoring force is bigger, and also if I go to the other direction, the sign changes correctly. And also, if I have, for example, velocity-dependent damping, I also get a derivative force as well. So if I have a really fast change, I have a really fast or a big restoring force here. Now, regarding the issues that I've pointed out with the classical control loop, so what about the sensors? Well, there are no sensors whatsoever, so there's no problem with noise, with drifts, with aging, and so on. So that's solved very elegantly. What about the delay? Well, this works literally in real time. It just obeys the laws of physics. There's no artificially introduced control loop. So it can be a very dynamic system and still it would work sufficiently well enough. And the final point is, and I think that's the most elegant part of the solution, is this energy that you have to provide to bring this ball back into its desired position is actually provided in this morphological computation setup, provided by the perturbation itself. So if I have a big force applied as external perturbation to the system, I get a lot of energy stored in the spring, and this energy will be then used to bring it back into its position. So it's very energy efficient. And even if there would be friction, some kind of losses, compared to the setup in a control loop, this additional energy that is needed for a morphological combination approach is much, much smaller than the one with the classical feedback loop. Now, if you look even closer, you can see that actually, if you have a velocity-dependent damping and stiffness function, and they're both linear, you actually have a PT controller, proportional derivative controller, implemented in the morphology of a system. Now, looking at these two things, just two different solutions, let's put it this way, they're both actually doing the same computation. They are reading out the position, comparing it to the reference point, calculating the error, and then calculate the appropriate force based on this error. It's a very simple computation, but it's for you to understand what morphological computation is from this viewpoint. Now, while the first computation is actually implemented in this external artificial controller loop, in the second case, this is implemented in the morphology, in the structure, in the dynamic properties of the system itself. So it's a very elegant solution. Of course, there are certain drawbacks. So we are basically outsourcing this computation to a physical system, which means, of course, we are losing some kind of flexibility. For example, if we want to change the side position to a different one, we would have to change the point of attachment or even have to change the spring itself. While in the upper case with the classical control loop, you simply provide a different reference point. So the first feedback control loop is very generally applicable. So you can even change the control of your nonlinear one or a PID controller, while below you have more constraints because you've already outsourced it to the morphology. But of course, there's a solution that you change the morphology, that you implement some kind of mechanisms to change it, to make it again more adaptable to new situations by doing that. So you can change the computation by changing morphology, and that's exactly what we consider as morphosis. So you can increase the field or range of possible applicable positions and solutions by adding some additional mechanisms. And we can see that in nature as well, and we want to have that in robots. Now, one way to have a look at that is by using the notion of a attractor landscape. So this comes from dynamical systems and control theory, specifically, where you say that you can define around the point of equilibrium some kind of a landscape which defines of how fast I approach or converge to this point of equilibrium. So this is a way to see it in a very abstract way. So I'm not saying that the body looks like this, it's just an abstract representation to make it easier to understand and also to come up with new ideas how we could implement morphosis. So what we have here is basically some kind of landscape which is shaped by the morphology. For example, in the puppy robot that Fabi showed previously, we have the spring, right? So it shapes there's a certain point of equilibrium, and if there's some small perturbations coming from the ground, from the impact, basically the spring is able to cope with that, and it has this attractor landscape to bring it back into its desired position. So there are forces which are defined by this landscape. And one could say, well, this is basically defining a controller, in this case a mechanical controller. It's exactly the same what I've showed in the previous thought experiment. Now, this could be defined as some behavior that is predefined by this morphology. Now, if the morphology is complex enough, you could imagine that you have a body which has multiple attractors. So you can have different behaviors, different controllers, all implemented in the same morphology. So you can basically move from a different point in the state space to another one, and then you have a local minimum which basically keeps you in this kind of setting. Now, how do you change now from behavior A to behavior B? I guess that's quite straightforward if you look at it from that point of view. Well, you simply have to push the system, in this case the ball, just into the right direction. And the really beautiful thing, it's a very simple change. It's a very simple control change, right? Because there's no precision needed. It just has to be big enough that you get over the hump, and small enough that it doesn't jump all the way to the other side and doesn't get into the desired behavior B. But even the direction doesn't have to be very precise, because the rest is basically done by the morphology, by this attractor landscape. If it's over the hump, I just can release the force, and it just attracts by this landscape into its new state, desired state, which is defined by this right side landscape here. So that's very, very powerful. The rest is basically done by the morphology. Now, the controller can be simple and also only temporary. Just when we switch, we need this controller and this energy, and then we can be again in the passive setup. Now, this is not yet morphosis, right? Because that's the same morphology. We are not actually changing the morphology, but we just have simply, in a complex morphology, implemented two different behaviors. So how would it look in morphosis? Well, you have a behavior A, and then you have, for example, a possibility by changing one parameter by a very small motor, for example. You change the center of mass, for example, which means also when you change the morphology, you also change the landscape. So you reshape the landscape in a continuous way, and you do that until you come into a new landscape, which is this behavior B. So the red one does not exist there anymore. It's just the new one, which is here denoted by B. And that's what we call morphosis. Switch between these two different attractor landscapes, so to say, by having ideally a very small parameter that has to be controlled. So again, this control of the switch from A to B can be very simple and is only temporary. We just do that, for example, if we have a new task at hand which needs us to use now behavior B instead of behavior A, or we have a different environmental condition, the friction changes, so we need a different limit cycle, for example. Now we switch, and then we can switch off this controller because the morphology itself basically takes over and controls it locally at exactly this new behavior. Now, what kind of control or what kind of behaviors we can consider here? Well, it has been very abstract so far. It could be just simply switching between two different controllers. So this could be like the PD controller that I showed with the spring mass temper system. You simply change the stiffness. You have variable compliant actuators which can change the stiffness, and then you have a new stiffness, and then you switch it off. In puppy, for example, this could be useful that you change the stiffness from the front and the hind legs if you walk up a slope, for example. But it could be more complex. You could also switch between different limit cycles, depending again on the new situation. Maybe this limit cycle for the locomotion is better than the other one, and then you would have to switch. And actually, there is some hypothesis that in cockroaches, where the bandwidth from the brain down to the actual actuation locomotion system is very, very low, but cockroaches are really good to overcome obstacles. So there's a theory that if you have the antennas, it's able to detect a step in front of it, for example, which doesn't change actually the control of the system, but change the angle of the shoulder here to different position, and you use the same controller and now to overcome the obstacle. And when you're on a flat ground again, you just go back to the old situation, behavior A or limit cycle A, and you do the same thing over again. But you can get even more complex. You could switch between limit cycles and reaching. You can have, for example, bifurcation. That's very interesting. Locomotion, then you see something, and then you switch from a limit cycle to an actual reaching movement. Again, this could be very easily done by changing just one parameter if the morphology is clever enough, by exploiting the idea of morphosis here. Now, like I said, if I have locomotion, you might have already guessed that that's not just a passive morphology or morphosis that we have going on here, but you have to provide some energy. So you can imagine a system that gets some kind of very simple control input, like the puppy robot. I think that's a really good example. It's just a sinusoidal function, and the rest, the controlling and dealing with the rough terrain, is actually done not by this abstract control signal, but rather by the morphology itself on a lower level. So we have a simple control input. It could be even a constant velocity, right, rotation around. And if you have a crank slider mechanism, for example, you can get that translated in a very complex endpoint trajectory. Now, this results in behavior A. And if I now change with some pre-designed mechanism, with some morphosis mechanism, I change a little bit the morphology, I get, with the same control input, a different behavior B, like a different limit cycle, for example, or the other examples that I've showed in the previous slide here. Now, and the idea would be you want to design it in such a way that this change is very simple. So you don't have to control 10 different parameters in order to make this change, but you have a mechanism where you have a very low dimensional variable, maybe just one dimensional, and you just increase the value a little bit, and you make the switch. And the rest, again, the stabilization, the robustness comes from this new morphology and from this new behavior B. And actually, that's possible. And I would like to share with you some examples, or actually it's one work which is quite complex and has been published in 3 different publications and has been done by Francesco Corucci, who's also from BISA. And he did a really cool thing. So what we had at the beginning was this octopus-inspired robot, again, from BISA here. And so it was bio-inspired. The problem was the design wasn't optimal. The morphology wasn't optimal. It was locomoting in a quite nice way, but not really fast. And we wanted to improve the design. So what we wanted to have is actually a simple control, which controls all the 4 legs here. So this is a very simple crank slider mechanisms, and we want to have a clever morphology. So we have the right parameters in order to have different behaviors by having the same simple controlling point. So that's exactly what I've shown in the previous slide, where we have a simple control, the morphology changes, and then you get a different behavior depending on the morphology. So we talk here about a morphology-induced behavior, as we call it. Now, of course, we didn't do that on the real platform, but we used a simulation and we used genetic algorithms. So in order to see how complex it actually was, so you can see all the parameters that we've considered in our GA. And just to give you a couple of examples, we had the center of mass, for example. We have the stiffness and damping parameters for the 4 legs. We have the center of buoyancy. And the blue circle, this Peter, is very interesting because this is going to be the crucial parameter for the example that I'm going to show. This is basically the angle of the center of buoyancy compared to the rest of the body. So what we did is we didn't optimize the body, for example, for locomotion to move as fast as possible, but rather we used a different approach, which is called novelty search. So we optimized for novelty in the sense that we want to find as many new designs as possible. So it got the high value for the cost function, or a negative if it's a cost function, of course, if it was a new design and it has a new behavior. So we wanted to try out as many different possibilities. So we ended up with a huge set of different morphologies, again, with the same control input, which resulted in a whole set of different, very robust behaviors. And I show you just 3 for the sake of the time constraints we have here. So these are abstract representations of our models that we found. So the first one we call the running robot. So the front and hind legs had different functionalities. The hind leg were bushing in the water, so we have was more for the swimming motion, while the front leg was actually jumping on the ground and was running on the ground. The second one didn't have any hind legs at all, just front legs, really strong ones, and they were used for swimming in an upward movement. And the final one was, for example, with very strong back or hind legs and no front legs almost, and this was used to hop on the ground. So you had different behaviors by different morphologies. Again, the controllers were all the same. The control signal was a very simple sinusoidal function for all 3 examples of that. The question was now, if we have all these designs, how can we now change and switch between the different behaviors? So what is the morphosis that we can use to switch, for example, from running to swimming? And the idea was, well, we wanted to find from all these different behaviors 2 behaviors which are very far away in the behavioral space. So it's not running and very similar to running, but running and swimming. So it's very different behavior. But at the same time, for this different solution, we want to find 2 which are close in the morphological space. So ideally, there should be just one parameter which is different that we then can change to switch from running to swimming, for example. So we're running a search algorithm on all the different solutions that we had, and we came up with a couple of designs where we simply had to change one-dimensional parameter in order to switch from very different behaviors. Again, the controller stayed always the same, and the switching was just temporary. We switched the parameter, kept it constant before and after the switching, and since we had these attractor landscapes defined by the morphology, it was attracted to this point where it had this limit cycle by providing this very simple input, and it was robust. So you could even have smaller perturbations and it would stay there. And if you just switch it back, it came back again. So here's at the end, you can see the graphical representation of this design that we had. And on the upper graphs, you can see the center of mass position. So X is the forward velocity, forward position, so the horizontal position, and Y is the vertical. And you can see at time step 6 in this case, in this graph, we switched one single parameter, which was exactly this beta parameter, where I said, well, we just changed the angle of the center of buoyancy, and by keeping the rest the same, the controller the same, and all the other parameters of morphology the same, it switched in a very robust fashion from this running behavior, hopping running behavior, into a swimming behavior upwards. So that's very, very nice. And again, if you switch it back, it falls down to the ground, and it's very robot. It finds its way back to its other behavior, which is behavior A, behavior B. So it was able to switch between running and swimming. And finally, I would like to show you the video to see that. So Nathan, if you can please start the video. So what you can see now, first in this running behavior, maybe can you stop? Nathan, can you stop and pause? Yeah. So you can see when it's up in the air, you don't see the springs, and when it touches the ground with the front leg, the simulation adds the springs there because it has to simulate the contact here. So it's a compliant contact. And you can see most of the front leg touches the ground, and the back leg basically just gives us this movement to move forward. So Nathan, you can go on again. Thank you. That's the running. And then we switch one parameter. So this buoyancy point goes a little bit back. And what you can see is now swimming behavior. And then we switch it off again, and it fell again back to the ground and came back to behavior A, to this running behavior. Okay, you can stop now. Thank you. So what we saw is basically just a small change in morphology. If the design is clever, we can induce this morphosis and change the behavior completely by keeping the control the same. So that's all from my side. So thank you very much for your attention. And if you want to see more videos, more information about how we did it, contact Francesco Corucci or have a look at our papers from Gecko, ICAR, and ECAL. Thank you very much.
Thank you. We are a bit short of time. I just want to say two things. One is that actually Francesco Corucci was the very first interesting thing that Francesco did was actually a koan in the Shanghai lectures. So he did a famous, very nice koan project 2 or 3 years ago. The second thing is that so how but maybe it's better that we will discuss offline or in another occasion because we are really short of time due to me and to a lower extent. How you relate, can you explain a bit what you see as a difference between morphological computation and morphosis? Because I would see morphosis as a special case of morphological computation. But
yes, you can see it as that, and I would even agree with that. That's why I also said it's the next level, right? And I don't say it's better, but I'd say it's a little bit higher in the hierarchy, right? I would see like a morphological computation, like this very simple local control there, in this case. And the next step is if we change between different types of morphological computation, like for example controlling a limit cycle or controlling a reaching movement, this is controlled by a high-level controller, which is a morphosis. So it's a little bit a step in between this abstract cognition part, which is the brain, and the very basic mechanical part, which is the morphological computation part. But you can include it, right? It's a special type of morphological computation. I guess you can say that, yes.
Okay, thank you. Sorry.
Hi, thanks for the talk, very interesting. I would like to know, firstly, if you tested if the motion was robust against the environment, so if any stream in the water changed the behavior quickly, and secondly, if the behavior from the simulation be easily transferred to the real world, the real robot we had in that water tank.
Yeah. Well, regarding the first question, yes, that was the main idea, that basically you have a robustness. And because if you want to switch between these two different behaviors, right, you need this attraction to this new situation. Because the morphosis parameter doesn't say that it has to go there. It just changes it and the morphology basically takes it over and finds this new attractor where it tries to stay. So it's robust in that sense. And the second question is, we haven't implemented it in the real robot, but of course that was the plan, the original one. It was a little bit lack of time as well, but all the parameters that we considered in our genetic algorithm that we optimized for are actually real parameters from the original real system. So yeah, that would be the next step, and interesting to see if we actually can translate these results to the real robot. Yeah.
Okay, thank you.
Okay, thank you. So maybe now we can have a 3 minutes break when we start with the next speaker, because we are a bit